Our tests of hypothesis to this point have been about testing a population mean. Sometimes that mean was a proportion. Sometimes the mean was in a more general unit. We've done right-hand tests, left-hand tests. So far we've talked about looking at standard normal test statistics when the sample size is large. And for the most part, whenever you're looking at a population mean and the data are not proportional, or not, you're not doing a test on proportions, but just a generic hypothesis test about mu, most often what you're going to see is a t-test. Okay, because you know as the t-test, as the sample size gets larger, that t-distribution approaches a normal distribution. So that 30 we started with, don't worry with that so much. You can just use t. Where we can use the standard normal, provided we have an adequate sample size, is on the population proportion. It is not the t-distribution if that sample size condition is not met. There are some other techniques we have to do if the proportions if the data that generate the proportions are not large enough in sample size. So in addition to those population parameters, we can also look at hypothesis testing about a population variance. Okay, so how variable data are, what's risk associated with it, the ability of being able to estimate within a certain number of units, such as one of our questions before starting this. All right, here I'm just setting this up as a two-sided test for a discussion point. Okay, since sigma squared is a function of squared observations, the standard normal distribution or the t-distribution applies, because what happens with standard normal? Standard normal distribution assumes that we have both positive and negative values, okay, and we're measuring in whatever the units are. Variance is measured in squared units, okay. The test statistic is given by this quotient, sample size minus 1 times the sample variance divided by the hypothesized variance. This is the Greek letter chi, so it's a chi-square distribution. A chi-square test statistic and a chi-square distribution. And the chi-square distribution has several applications. In this application, again, the degrees of freedom are what we saw last time, which is sample size minus 1. All right, we'll look at some other applications of the chi-square distribution later in this course, and we'll have the degrees of freedom will depend on the type of data we're testing. Okay. What does the distribution of a chi-square random variable look like? Okay, it is lowest value here at 0, and it is an asymmetric distribution. Okay, so that's what chi-square roughly looks like. All right, so the chi-square distribution changes shape as the degrees of freedom changes. Similar to what we talked about with the t-distribution. As the degrees of freedom increases, the chi-square distribution widens. And so to demonstrate that, we have the solid line drawn in here. If I draw in another chi-square distribution, some kind of an asymmetric curve right through my label. Okay. Solid line in red is our first degree of freedom measure. The dashed line in purple is degrees of freedom 2. And it is the case that degrees of freedom 1 is less than degrees of freedom 2. So as the degrees of freedom changes, remember the area under both these curves has to be 1. All right, so as the degrees of freedom gets larger, this distribution gets pushed out away from 0, so they all still come up to 0 here. As the degrees of freedom get smaller, this distribution becomes more compressed against the vertical axis at 0. Okay? All right, if we look at this test statistic up here, all right, if the null hypothesis is true, and we're testing, it's up off screen, let me slip this. If the null hypothesis is true and sigma squared equals sigma naught, equals sigma naught squared, okay, then what? Whenever we compute our sample of whatever size it is, then our sample variance should be close to sigma naught squared. Agreed? The null hypothesis is true. Our sample data should reflect this condition. We're very close to it. We know it's never going to be exact, but we should get close to it. If that's true, if s squared is close to sigma naught squared, what happens to the value of chi-square? So this chi-square value, n minus 1 times s squared over sigma naught squared, this quantity up here I just repeated, so that way we can pull this out. Okay, so if s squared is close to sigma naught squared, that's right here. That's going to mean that part of this computation is close to 1. All right, so if h naught is true, then the value of chi-square is close to what? It's close to the degrees of freedom, is close to the degrees of freedom equals n minus 1. If the null hypothesis is false, then what happens? And kind of just the opposite conditions than what we wrote up here. If the null hypothesis is false, then our value for the population variance is not this sigma naught squared. Then what can I say about chi-square? All right, so let's just kind of take both sides of it. So suppose the true value is larger than sigma naught squared, the true value of sigma squared. So suppose the true value of sigma squared is larger than this. Then s squared is going to tend to be like what? It's going to tend to be larger than sigma naught squared also, isn't it? Okay, and so as s squared gets larger, what happens to this? Chi-square gets larger. Okay, what happens if the true value of the population variance is much smaller than sigma naught squared? Then this ratio becomes smaller and smaller. What's the smallest then chi-square could be? It starts getting closer and closer to 0, doesn't it? All right, so here if the null hypothesis is false, then the value for chi-square is either very large or close to 0. The critical values of chi-square are found on page 624 in the Freund and Wilson second edition. And in third edition, there were Freund, Wilson, third author Moore. 7. Say that again, please. 728. In both cases, we're looking at table A3. So it's easier to remember table number rather than page number. Okay, so the differences between the two textbooks is just the format of the table here. Okay, if we look at that real quick. The column headers says chi-square values exceeded with the given probability. So the column headers are right-hand area in both cases. It's here in both cases being when these right-hand areas are quite large. Here's the middle or the median of the distribution, right? Half of it to the left, half to the right. Okay, then we start getting into smaller values for right-hand area. That's much different than what we've seen before. So the format of this is very much like the t-table, but the t-table didn't have these very large values here. And one of the reasons it didn't was why? Because the t-distribution is symmetric about 0, right? So the values in the left side of the distribution, we could just take the negative of the opposite sign of the positive values and work with that. Chi-square distribution, though, a little different. Okay, so what we're looking at, regardless of which edition of the book you have, is that you end up with some values here where that column header P is close to 0.9 or greater than 0.5, so you have all this area, or you have images that look like your chi-square distribution and you're looking at small areas. Okay? So in these cases, these values in here are things like we're looking at right-hand area 0.99 or 0.995. So that's the kind of thing we're looking for. If we can find the right-hand area, then that means then we know this left-hand area in this instance would be 0.01. Okay? Now, having all this information, then we can go back to that tabular arrangement of hypothesis testing situations. Whoops. Had 2 pages stuck together. Now we go to our tabular arrangement of hypothesis testing situations. You have a question?
For chi-square, is 1 the complete area under the curve?
Always. It's a probability distribution, so the area under the curve is 1. All right, so here again I have it set up. 2-sided test, right-hand test, left-hand test. All right, we've already familiar with the pattern. Our chi-square test statistics, these are exactly the same. This one I printed 3 times instead of just drawing the arrow down. So these are the same no matter what. All right, 2-sided test, 2-sided rejection region, right side test, right side rejection region, left side test, left side rejection region. Okay, so what's going on here? And this right here, our 2-sided test, we're going to look at our chi-square distribution defined by the degrees of freedom. So here it says the right-hand area is alpha over 2. Over here it says the right-hand area is 1 minus alpha over 2. So if the area to the right of this one is 1 minus alpha over 2, then this left area in here must be alpha over 2. Agreed? So this 1 minus alpha over 2 is not just from here to here, but from here all the way out to infinity. Okay? Mark it that way maybe. It looks a little better. All right, so what we're saying in this first one is we're going to reject for values of chi-square that are very large or very close to 0. That's in the 2-sided case. In this case, it's only going to be for what? Chi-square values that are very large. The alpha is over here. And in this last case, we're going to find the value such that this is 1 minus alpha, so that must mean that this left-hand area is alpha. All right, so in this case, if alpha is 0.05, let's say, then this is 0.95. That's why we need those column headers we saw in there that had the very large values, close to 1 probabilities. It's very different than we saw in the case of the t-distribution, right? Whenever we talk about hypothesis testing for a population variance, of course, it's always the case that we have a random sample and that we're making the assumption of a normal population here. Okay, and then for this application, our degrees of freedom are sample size minus 1. Okay, so let's hang on here and look at an example. We'll keep our formulas handy. A manufacturing process is under control if the variance of the product is kept small. A machine produces metal plates with a mean diameter of 7.5 millimeters. The variance of the diameters cannot exceed 1 square millimeter. If it does, the machine must be repaired. A random sample of 31 plates is collected, and the sample variance is equal to 1.62. Is there evidence that the process is not under control? Use alpha equals 0.05. All right. How do we translate this question into H0 and H1? Okay. So here we can write the process is under control if the variance is kept small. We want it to be smaller than 1 means the process is under control. Out of control means the variance is too large. So we're trying to, is there evidence that the process is not under control? That means is the variance large? The variance is small. I'm great with that. All right. So what we're looking at then is the population variance, does it exceed 1? Okay. The null hypothesis is that this variance is less than or equal to 1, or you could just write equals 1. All right. So the translation of variance greater than 1 is that the process is not under control. All right, we're going to conduct our test at the 0.05 level. What sample information do we have? Well, from the sample of size 31, we have that the sample variance is equal to 1.62. What is 7.5? What is 7.5? We're given some other numbers here. So what are they? That's the target mean, mu naught, isn't it? Do I need that for this question? Do I need y bar? No, not if I have the variance computed already. I don't need y bar either. So if I had y bar, that's not a bad thing, but I don't need it. Okay? All right, so what is our test statistic? We compute chi-square, pull our formula back over, put it back underneath. This is the scenario we're in, the second one, off of the previous page. All right, sample size minus 1 is what? We're looking at 30. Sample variance. This is already variance given to us. If it's standard deviation, then we have to make certain we square that. But it's already variance as we're looking at it. So that's 1.62. Oh, and life is easy because sigma naught is 1. Sigma naught squared is 1. Okay? So when we compute this, we end up with what? $48.6. Okay, so remember all this is in squared units, and then we've taken that, and so the general feel of things we had for a t distribution and a z distribution, those test statistics, between 2 and 3 when things started to be significant, doesn't happen with a chi-square. That magnitude is greater. All right, what's our rejection region? We're going to reject the null hypothesis if what happens? If our chi-square test statistic is large only. Agreed? So if chi-square is greater than or equal to the chi-square determined by right-hand area of alpha, which in our case is 0.05, and the degrees of freedom are equal to 30. So we need to go to our chi-square table, go to the row for 30 degrees of freedom, and then read over to the column headed by 0.05. Say again, please. 43.773. Does everyone agree? All right, so how did we do? What's our decision? The process is or is not under control? Is not. All right? So the simple conclusion that I don't want you to write is that you're rejecting the null hypothesis. I guess if you put it over to the side, I'm not going to care, but you got to have the interpretation and the context of the problem. All right? So the process is not under control. And repairs are needed. We conducted our test at the 0.05 level. What else do I fill in here? Our calculated test statistic, right? I heard chi-square with 30 degrees of freedom is equal to 48.6. And then our p-value. Here we stop again. How do we do p-values? It's going to look very much like that for a t distribution in this side for a right-hand test. All right, so I want you to go to the table, stay in the row for 30 degrees of freedom, read across until you find the two values between which 48.6 falls. Read your column headers. All right, from your chi-square table, you're in the row for 30 degrees of freedom. The two values you should find are 46.979 and 50.892. Agreed? Those column headers are 0.025 and 0.01 respectively. But we want to write the smallest p-value, or make sure we get our inequalities right. Most usually we'll write the smaller number to the left. And so the p-value is between 0.01 and 0.025. Again, in this application, when I ask you for a p-value and you have to come up with an interval, I want the narrowest interval you can. Just don't tell me p was less than 0.05. Okay? I need the narrowest interval. All right? If we have other software computing the test, it may compute it more exactly for us. But as long as we're using these tables, this is what I want. Okay? We don't double this because it's not a two-sided test, just in the same as we did before. Agreed? like we did with the t-distribution, let's have a little practice, okay? Because the left side of this distribution is can be a little more tricky, okay? All right, so suppose we have an alternative hypothesis that sigma squared is strictly greater than 24. We have a sample size of 28, and we computed chi-square of 44.3. What is our p-value? Right-hand test, right-hand rejection region. Okay, so that means when we compute p, the p is equal to the probability of seeing a chi-square value greater than or equal to, either one is okay, 44.3. I need one other piece of information. What's the degrees of freedom on this chi-square? We're given sample size is 28 for this application. We need to subtract 1 to get degrees of freedom. So this should be a chi-squared value with 27 degrees of freedom. All right, so over here at the side, we can draw our pictures. I guess I could have just drawn the right tail. I can stretch things out a little bit. Total area is 1, despite what my picture might suggest. Okay. All right, nothing's going to be to scale here because of what I want to do, draw in the tail area here. All right, so you need to go to the row for 27 degrees of freedom, read across, find the two values between which 44.3 falls. When you read across, you come to, this is where the scale's not going to make sense, 43.195, and it determines a right-hand area of what? 0.025. The next value, 46.963. And it determines a right-hand area of 0.01. Our calculated value is in between here. All right, so we know that this probability here is bigger than 0.01 but smaller than 0.025. Agreed? Which is the same p-values we reported in the previous problem. All right, now if we have a left-hand test. All right, so what's our probability? If we have a left-hand test, we have a left-hand rejection region. A more extreme score is to the left, so we want left-hand probability. All right, so our p-value is equal to the probability of our chi-square test statistic being less than or equal to 13.2. Right? That's what was calculated. The degrees of freedom are equal to 22. All right? So where we're at in the distribution here, I'm not going to draw it all. I'm just going to we're going to focus it in right down here, so it's going to look a lot bigger. Okay, so here's our chi-square distribution that's where we're at close to 0. Okay, I want to go to the row for 22 degrees of freedom, read across, find the two values between which 13.2 falls. I have 12.338 The column header for 12.338 is 0.95. So that means that it has a right-hand area of 0.95. So that means its left-hand area is what? .05, right? Total area is 1. The next one is 14.04. That's the closest to 13.2 on the other side. .041. The column header for 14.041 is 0.90, so that means this right-hand area is 0.90, which means then the left area is 0.1. Our 13.2 is in the middle here somewhere. All right, so we want the left area associated with 13.2. And what is it? Pardon me, 13.2, our x here, has a left area bigger than 0.05 but smaller than 0.1. Now, is there ever a time that you would report a p-value here? Sure, if we would have done a right-hand test and calculated this value, we would want that right-hand probability or right-side probability. Okay, is it ever possible for that to happen? Right. If you have, so the idea is if you were testing whether or not the variance were greater than 57 and you have absolutely no evidence of it. In fact, your evidence is on the much further to the other side. Okay, that's how you're going to get those p-values very close to 1. Does that make sense? All right, we're going to look at a two-sided test here. So I have the chi-square test for testing the variance is whether it's equal to or different from 82. We have a sample of size 17 and we compute 31.8. All right, so for a two-sided test, I know my rejection region is to reject if chi-square is very large or very close to 0. How do I know where I'm at? Okay, so first of all, we know we have 16 degrees of freedom. Okay, do we want to compute the probability that chi-square is larger than 31.8 or smaller than 31.8? Well, on those two-sided tests, you have to figure out which half of the distribution you're in. Okay, so let's take a second. Go to the row for 16 degrees of freedom because we're trying to figure out where we're at. So we've got a couple of blanks in here, our sign to figure out, and then whether or not we're multiplying by 2. All right? So whenever you draw this picture, go to 16 degrees of freedom, go over to the middle column, 0.5 column. What is the median of this distribution? $15.338. Agreed? All right, so somewhere over here, we know that 15.338 is the median. So that means then that this area is 0.5 and this area is 0.5. So we're in the right-hand side of the distribution, clearly. 31 is much larger than 15. All right, so we want to keep going across, then we want right-hand area is what that tells me. More extreme is area to the right. Okay, so we could stay in that row. We could have not marked the median, but just kept going. So between what two values is our calculated value 31.8? So we come over here. The first one is equal to the closest value, chi-square value on the left is Right, 28.845. And it determines a right-hand area of what? 0.025. The next value is 32, and it determines a right-hand area of 0.01. Everyone agree? Take out this arrow here so it looks a little better. All right, our 31.8 is in between those two. So what would you first of all, we have to then report we're looking at right-hand areas. Agreed? Because we're in that right side of the distribution. We multiply by 2 because it's a two-tailed test. So what we found over here, this 0.01 less than the other side 0.025, what we found here is not p-value but 1/2 of it, right? We haven't multiplied by 2 yet. So that means our p-value is between 0.02 and 0.05. Is everybody okay with that? Then in a similar way, we can look at a two-sided test. If I've done one in the right half of the distribution, you can probably guess this one's going to be in the left half, but we'll verify why and what's going on. It does merit some attention. All right, so we do the same thing here, except I'm not going to draw the full curve. I'm just going to enlarge this area right around 0. We want to look at a chi-square distribution with how many degrees of freedom? 24, because our sample size is 25. Okay. When you go to the row for 24 degrees of freedom in the chi-square table, the median is 22.337. So that is, if we go to the 0.5 column, we have 22.337. We are certainly to the left of that. So that's why we need to be in the left side of the distribution. I didn't write that down here because I didn't draw the full picture. But we could draw a picture like this and mark the median and then locate where we are with respect to the median. Okay? So what is it I need? If I'm in the left side of the distribution for a two-sided test, then I need left area or right area? I need left area. Okay? So our p-value is going to be equal to, multiply by 2 because it's a two-tailed test, the probability of a chi-square random variable with 24 degrees of freedom being less than or equal to 11.6. So again, staying on the row for 24 degrees of freedom, read across, find the two values, the closest two values between which 11.6 falls. They are where? So the first one we get, I have 10.856. Do you agree? It determines a right side area of 0.99. So that must mean the left area is 0.01. The next one over is 12.401. It determines a right area of 0.975. And it determines a left area of 0.025, since those areas must add to 1. Our 11.6 is in here. So what do we report? All right, that the left area is bigger than 0.01 but smaller than 0.025, and that left area is 1/2 of the p-value. All right, so 0.01 is less than 1/2 of the p-value, is less than 0.025, and if we write the p-value, then it must be between 0.02 and 0.05, just like the one above it. Most common wrong answer on this question is to tell me that the p-value is between 0.975 and 0.99, or, well, it's a two-tailed test, I've got to double it, so the p-value is between 2 times 0.975 and 2 times 0.99, which is too big, right? Then you're telling me the p-value is between some values very close to 2. What is the common sense check for p-value? It's a probability. It has to be between 0 and 1. So if you're computing p-values that are in excess of 1, you probably needed to look at the complementary probability and then double that, but double check all your answers. Okay? So it's possible in these one-sided cases that we could have ended up with, even though it's a right-hand test, that we could have been in the left side of the distribution and needed that big right-hand area. So it's possible for us to get p-values between 0.5 and 1 when we look at a one-sided test, because that means your evidence is exactly the opposite in the other side of the distribution. You don't have any evidence to support your research question. You're not even close. All right. Likewise, this one we could have been in the right-hand side of the distribution when we were actually wanting to do a left-hand test. So that could happen with your sample data. Okay. But that's how you would still you can still report a large value there. All right. But what helps you on these two-sided tests in particular is figure out where the median is, and are you to the left or to the right of it, so you know. You want to compute the smaller area for the two-sided test and then double it. Does that make sense?
Not have an equal sign.
The greater than or equal to, pardon me, it doesn't matter, because for a continuous distribution, the probability of being equal to a single value is 0. So it doesn't matter if you write here greater than or equal to, likewise down here, or I could have put those strictly less than. We can also talk about a confidence interval for a population variance. And I didn't write it on here, but should have. Our conditions or assumptions. Of course, that we have a random sample. And second, that we have a normal population. All right, so what this looks like is just a rearrangement of that chi-square test statistic, which if you think about our other confidence intervals, they were just a rearrangement of the expression for t or z. Okay, so here now in the denominators, we have critical chi-square values. All right, the numerators are exactly the same, degrees of freedom times the variance estimate, and so it's not plus or minus because we have everything's in squared units. The chi-square distribution is certainly not symmetric; it's very skewed. All right, and so that when we look at these values, that's why we're not doing the plus or minus, and also because chi-square values are all positive. Where are these on the distribution? Because when I first looked at this in your position, to me it looked like these denominators were wrong. I thought they appeared switched, but they're not. Okay, so let's look at where those critical values are. So what we're finding here, this time I want the chi-square distribution with n minus 1 degrees of freedom. All right, the subscripts, whenever you see alpha in a subscript, if it's alpha over 2, my notation, that is always right-hand area. Okay? Your textbook is almost everywhere the same. I think there's one point where they don't subscript. All right? But my subscripts, whenever you see alpha or alpha over 2 in a subscript, that's right-hand area. Okay, now be careful, because when you move to other textbooks, they may not use subscripts, but they may put it in parentheses, and they specify an alpha or a function of alpha. And so depending upon the textbook and the notation, you have to be very careful, because some of them could be left-hand area. Okay, so as we're doing it in this class, those expressions in the subscripts are always right-hand area. So that way you should hopefully never be confused. So that's why we can see those 1 minus alpha over 2's, because those are those right-hand areas that tend to be large. Okay, so for us, alpha over 2, alpha is small. So when we look at chi-square, alpha over 2 is over here, and that determines a right-hand area of 1 minus alpha, of alpha over 2. This one, chi-square 1 minus alpha over 2, that says that this left area is alpha over 2, and the area to the right, all the way and past this, keep going, is 1 minus alpha over 2. Okay? So don't let the subscripts goof you up. It's always right-hand area. Okay? So now then, when you look up here, the numerators are identical, so chi-square 1 minus alpha over 2 is a value close to 0. Okay, or closer to 0 than the other one. So here I'm taking a number, and of these two pieces here, this is the smaller number. So when I take and divide by a smaller number, I'm going to get a larger quotient. All right? If I divide here by something far to the right in the chi-square distribution, this number's bigger. So that means this endpoint is going to be smaller than this endpoint. Okay, so because those chi-squares are in the denominator, right? That's why the inequalities are the direction they are. Okay. So let's look one of those up, and I don't have to worry about, because of the notation, I automatically am going to be in the right side of the distribution or the left side of the distribution. I don't have to worry about making any sorts of adjustments on that. All right, a sample of 16 is drawn, and a sample standard deviation of 7.2 is observed. Find a 99% confidence interval estimate for the population variance. All right, so we're assuming normality when we do this, even though it didn't say that. All right, we have a sample of size 16. Our sample standard deviation is 7.2. And we want a 99% confidence interval, so if 1 minus alpha is equal to 0.99, then alpha must be equal to 0.01. So if we want a 99% confidence interval for the variance sigma squared, all right, what do we need to do? All right, sample size minus 1 is going to be 15. We are given sample standard deviation and we need variance. Again, be attentive to what you're given. That didn't go away with the first exam. 7.2 squared divided by, we need a critical chi-square value that determines what tail area. Alpha over 2, and alpha is 0.01, so this would be 0.005, and how many degrees of freedom? 15. Less than or equal to, or you can just write or strict inequalities here. Sigma squared, less than or equal to, numerator's the same, 15 times 7.2, only the 7.2 is squared, divided by a critical chi-square value with what right-hand area? If this is 0.005, then this has to be 0.995, right? Those two areas have to add to 1, and still 15 degrees of freedom. So we need to go to our chi-square table in our textbook, look up those critical values. Those numerators stay the same. On the left, what do you get In the row for 15 degrees of freedom, in the 0.005 column, I have 32.801. Less than or equal to sigma squared, less than or equal to numerator 15 times the quantity 7.2 squared, divided by what's our chi-square critical value from the left side of the distribution. So in the row for 15 degrees of freedom, the column headed by 0.995, I have 4.601. And what happens when we compute that? I have the interval 23.7066 less than or equal to sigma squared less than or equal to 169.0067. Did you get the same? Now, oftentimes, and we've made this point before, it's hard sometimes to comprehend variance because it's in squared units. It just seems too big, right? If your data are larger than 1, variance is just too big. All right, so when we look at this, these are in squared units, and you might think, well, that seems kind of large for the dispersion. Though we were only asked here for the confidence interval for the population variance, one could look at the confidence interval for standard deviation. And so if you are asked for the confidence interval for standard deviation, you first compute the confidence interval for the variance, and then whenever you want the confidence interval for sigma, take the square root of each endpoint. On the left, I have 4.8689, less than or equal to sigma, less than or equal to 13.0003. Okay, so just be careful what you're being asked for. So you don't have to do anything up here. You just have to work with the variance to get the interval and then take the square root. Now you can get both of these intervals as well as a confidence interval from you if you're using SAS in the univariate procedure. One of the options we had was CI basic. And so that's basic confidence intervals. And so those are the confidence interval for the mean, the variance, and standard deviation. And so that becomes a part of the SAS output in proc univariate. If you don't request it, you won't get it. Okay? Proc means does not compute confidence intervals for variance. It does confidence intervals and confidence upper bounds and lower bounds for the mean. Okay? We didn't look at the one-sided what's called a one-sided interval, a confidence lower bound or a confidence upper bound for variance. We're not putting that in the course at this time, but could we do it? Sure. What would you do? Well, if you wanted confidence lower bound, this is going to be alpha. All right? You're not going to do alpha over 2. If you wanted confidence upper bound, this is going to be 1 minus alpha. Just like you do in those corresponding hypothesis tests, right? Okay, you're not going to do alpha over 2, so you can get confidence upper bounds and lower bounds for variance as well. I just don't see that done as often.